up until now, we've mainly been studying first-order differential equations, and this is the general setup for a first-order initial value problem. You've got a differential equation and an initial condition. And for first order, the differential equation is only allowed to relate x prime, x, and t. What we're going to start looking at now is second-order differential equations, where you're also allowed to throw x prime prime into the mix. So these are really important because a lot of differential equations come from applying Newton's laws in some way, applying Newton's second law in some way. And Newton's second law is a second-order differential equation, right? Newton's second law says that, applying it in one dimension, so that we have one unknown function only, if x of t is the position of a particle, along one line of motion that it's allowed to move along a line, then Newton's second law says x prime prime, the acceleration, times the mass of the particle equals the sum of the forces. So here when I write F, that means the sum of the forces, the net force on the particle. And this doesn't really tell you much until you decide for any given situation what would be the forces. So I usually think of this as like a definition of force. This is what force does. It affects the second derivative of the position in this way. So, you pick a system. I'm going to throw in this gravitational force or this friction force or both, and you figure out what is the net force, and you stick that here on the right-hand side, and then you get a differential equation, which will allow you to make predictions about the position of the particle. So typically, or in general, the force can vary in time, for one thing. So you can have the force depend on time explicitly. For example, you're pushing on something, and you just vary how hard you're pushing in time. It can also depend on x. For example, if x of t is measured along, a line coming out of the center of the Earth, a ray coming out of the center of the Earth, then x represents the distance from the center of the Earth of a particle. And if you pretend that the Earth is a point particle, maybe you're talking about large distances or something, then the gravitational force due to the Earth on a particle is going to be some function of the distance of the particle from the Earth. So that would be an example. Anytime someone talks about a force field, where at different locations in space there's a different value for the force vector, that would be a situation where you've got the force depending on position. So depending on x, which is the name of the dependent variable, the unknown function. You can also have the force depend on x prime, and we'll see that in the case of damping. So like, think about air resistance. If you are driving, think about the forces on you. So you've got your thrust, as you're pressing the gas pedal, you've got, the friction force, the static friction force on the road pushing you forward. Let's just call that the thrust due to your pushing the gas pedal. That would be an aspect of the net force on you that depends on time explicitly, right? Like if you just press down on the gas pedal harder and then soften and then harder or something, then you're varying your force directly. You're varying the force on your car directly with time. On the other hand, the air resistance on you depends. It does also change in time, but not explicitly. You wouldn't write it as a function that explicitly depends on time. You would express it as depending on your velocity, right? If you're not moving at all, if your velocity is 0, then the air resistance force is 0. If you're driving very fast, the faster you drive, the stronger the effective air resistance on you. So this is Newton's second law in kind of a general situation and in one dimension. So notice we only have one unknown function, x of t, the position of a particle along a line. If we want to allow a particle to move around in a plane, to move around in 2 dimensions, we'd have to introduce a second unknown function, y of t. If we want the particle to move around in 3 dimensions, we'd have to introduce a third unknown function, z of t. This is something we'll do later, like towards the second half of the course. That would be studying not higher order systems, but higher dimensional systems. And what we're doing now is sticking with one dimension and just upping the order, meaning we're going to second order. So that's why I'm insisting that particles move along a line. Okay, so what changes with initial value problems? Well, in order to make a prediction as to what's going to happen given a first-order differential equation, you need an initial condition. Before you put down the initial condition, all you can get is a general solution. What about with a second-order differential equation? So let me get the Newton's second law context out of here. So let me remove the mass and just say x is the state of some system, and x is a function of time. Then this is what you have in general. X prime prime is going to be some function of time, x, and x prime. And it could be only a function of x, or it could be only a function of two of them or something. It doesn't have to involve all three, but it could. So what would an initial value problem look like? So you definitely need an initial condition, like this. But that's actually not enough. And you've already seen this with second-order systems that you have looked at back in week 1 when we were looking at differential equations that can be solved by just integrating. So you saw that if you have 2 derivatives, then to solve you have to integrate twice, and each time you integrate you get a constant, an unknown constant, and that constant is going to be part of your general solution. Then you need the initial condition to determine what that constant should be. But for a second-order differential equation, you'll have 2 unknown constants. One initial condition will be insufficient to determine 2 unknowns. Right? You need 2 equations to determine 2 unknowns. So a typical setup for an initial value problem is this. At a certain time t0, you could know what is the state of the system, and you could know the first derivative of the state of the system. And in fact, often people think of the state of the system as being given by not just the value of x, but the pair consisting of the value of x and the value of x prime. So, for example, if you're interested in tracking the motion of a particle, then to describe its state in a way that allows you to make predictions, you wouldn't want to just know the position of the particle, you would also want to know how fast it's going. Yeah, hopefully that's kind of intuitive. If you want to predict, if you want to use the differential equation to predict what's going to happen next, like say you have information at a particular instant in time, and you want to predict what's going to happen next, then you really want to know x and x prime, because that lets you evaluate this right-hand side here, right? Then you can determine what is x prime prime, and then you can use all that information, x prime prime, to determine how x is going to change. All right, so those are all different ways for me to motivate that the structure of an initial value problem is going to be like this now. It's going to require 2 initial conditions. Okay, so in the next videos we're going to look at where you might get some second-order differential equations, like specific ones that we're going to study in depth for the next few lectures. And we'll also look at how we can force things that don't look like the ones that we're going to study to look like the ones that we are going to study. So typically, Yeah, so typically in math and physics, you don't just find uh, you don't just find what problems you can. You don't just go to nature, find problems, and then uh, take them and be like, I'm going to solve this problem no matter what. Often it's the other way around. You look at the math and you go like, okay, most problems are hard. Let me see which ones I can solve. Then you work out the ones that you can solve. Then you go to nature and be like, okay, what can I force to look like these problems that I can solve? So it's kind of a little bit backwards, but it's still very amazing how effective that strategy is for gaining insight about even very messy systems.